Welcome to the Deep Dive. We're here to cut through the noise, help you get well informed, fast.
That's the plan.
And today, we're diving into something. Well, something that's all around us. It dictates what you wear if your flight's on time.
Even when multi-million-dollar satellites get launched.
Exactly. You know that Mark Twain quote, "Climate is what we expect, weather is what we get."
Ah, yes. A classic. And very true.
It really sums up our mission today, doesn't it? We want to understand that interplay, weather, climate, unpack the core elements.
And see how they really shape our world, our lives.
Mhm.
So yeah, our aim here is to give you a clear, sort of structured handle on these atmospheric things. They get mixed up a lot.
They really do.
But they are fundamentally different. We've waded through quite a bit of material to pull out the key insights for you.
Give us that fresh perspective on the air we breathe.
Precisely. The skies above us.
Okay, so let's unpack this then. Weather. It has this amazing ability to connect strangers, you know?
Huh.
Well, our sources paint this picture. Blazing hot day.
Yeah.
You walk into a building, step into an elevator,
Okay.
and you and a total stranger just simultaneously pull out handkerchiefs, mop your brow, share this hopeless look.
Huh. Yeah, I can picture that.
And then someone says, "It is so hot."
Yeah.
And instantly you've got a connection.
The universal icebreaker.
Totally. But what is weather really, and how is it actually different from climate? People use them interchangeably all the time.
They do, and that's where the confusion starts. It's a great place to begin.
Mhm.
Think of weather as, the atmosphere's mood right now,
Okay, it's mood.
or over a really short time. A few hours, maybe a day, perhaps stretching to a week. It's fleeting, always changing.
Like waking up to sunshine and then boom, rain by lunch.
Exactly that.
Yeah.
Or, one part of a big city might be sunny while another part's getting drenched.
Right.
That's weather. It's that immediate temporary state. It affects your comfort, your plans for the day,
Yeah.
cold morning, sticky afternoon, windy evening.
Got it. So climate then?
Climate. That's more like the atmosphere's personality.
Ah, okay. Personality, not mood.
Exactly. It's the general pattern of weather for a place, but averaged over a really long time. Typically 30 to 35 years.
30 years. That's a long time.
It is. It's based on decades of data, so it's much more stable, not really affected by those daily ups and downs.
So India has a tropical monsoon climate. That's a long-term thing.
Precisely. Or Antarctica has a polar climate. That long-term average lets us sort of expect certain general conditions.
And there are specific sciences for each.
Yes, absolutely. Meteorology studies the weather, the immediate changing conditions.
Okay.
And climatology studies climate, those long-term stable patterns.
That distinction.
Yeah.
Yeah, that makes a lot of sense. But okay, beyond just the definitions, why is understanding this difference really, crucial? How does it affect us in the real world?
Oh, the practical side is huge, especially when you talk about weather forecasting.
Right. The weather forecast,
It
it's
is
everywhere.
Absolutely everywhere. On your phone, TV, radio, websites, updated hourly, daily, weekly.
Even fortnightly sometimes.
Yeah. And think about who relies on it. Sailors, fishermen. Their safety, their livelihood depends on it.
That's
Travelers heading to high altitudes, they need good forecasts. Outdoor sports,
Yeah.
Imagine planning a big cricket match.
Oh yeah, rain can ruin everything.
Exactly. But then the stakes get even higher. Think about ISRO, the Indian Space Research Organization.
Launching satellites.
Right. They need incredibly precise weather forecasts for that specific launch site, that specific window. An unexpected gust could be disastrous.
Wow. I hadn't thought of that.
Or disaster management agencies like NDMA. They rely heavily on forecasts for heavy rain, snow, floods.
Preparedness.
Exactly. To issue warnings, get resources ready. This knowledge literally saves lives, protects infrastructure.
It really makes you appreciate what goes into predicting the skies. Okay, so these elements of weather, the ingredients you call them.
Mm-hmm. The conditions that describe the atmosphere at any given moment.
Our sources list 7. Temperature, air pressure, wind, humidity, precipitation, sunshine, and cloud cover.
That's the list. They're all measured regularly.
Let's start with the one we probably feel most directly.
Temperature.
Temperature. Simple concept, right? How hot or cold the air is.
Seems simple.
Well, yes and no. Your basic thermometer gives you the temperature now, but scientists use more specialized tools.
Like,
Like 6 is maximum and minimum thermometer. It records the highest and lowest temperature over a 24-hour period.
Ah, so you get the daily swing.
Exactly. That's the diurnal range of temperature, the difference between the max and min in one day, and you can do that over a year, too, for the annual range.
Okay.
There are also automatic recorders, thermographs, that draw a continuous line on a graph paper showing temperature changes over time.
And that white box you see at weather stations.
Oh, the Stevenson screen, yes.
Mm-hmm.
It's crucial. It's a slatted box, painted white, designed to keep the thermometers shaded from direct sun, but allow air to circulate freely. So the readings are accurate for the air, not just sun baking the instrument.
Precisely. That's where the temperatures you see in weather reports usually come from.
Makes sense. And units. Celsius, Fahrenheit.
Right. Most of the world uses Celsius. 0 for freezing water, 100 for boiling.
We learned that in school.
And then there's Fahrenheit, common in the US, 32 for freezing, 212 for boiling. India adopted Celsius officially.
And what about our comfort?
Well, our bodies run around 37 degrees Celsius, or 98.6 Fahrenheit. We tend to feel most comfortable apparently around 27 Celsius.
Which is why air conditioners often default to something like that.
Could be. It's that sort of ambient sweet spot for many people.
Interesting. Okay, from temperature, let's move to something, well, invisible.
Yeah.
Atmospheric pressure.
Ah, yes. The weight of the air.
It sounds strange, air having weight.
But it does quite a lot, actually, when you consider the entire column of air pressing down on every square inch of the Earth's surface.
So that's pressure.
That's atmospheric pressure. Force per unit area. And here's the thing. It's not constant. It changes based on location, time, and definitely height above sea level.
Right. Less air above you, higher up.
Exactly. Go up a mountain, pressure drops.
How do we measure this invisible force?
With a barometer. The classic ones use mercury, but they're fragile and, well, contain mercury.
Not ideal.
No. So the aneroid barometer is much more common now. It's quite clever. A small, sealed metal box with some air removed, creating a partial vacuum.
Okay.
As the outside air pressure changes, this box either squeezes in or expands out slightly.
And that moves the needle.
Precisely. It moves a pointer on a dial. No liquid, very handy.
What units do we use?
Usually millibars or embahole. Average pressure at sea level is roughly 113 millibiter.
So more than that is high pressure.
Correct. High pressure systems often mean stable, clear weather.
And lower than 1,013 millibiters.
That's low pressure. Often brings unsettled weather, clouds, maybe storms.
And like temperature, can you record it continuously?
You can. There's a barograph, which works similarly to a thermograph, providing a continuous trace of pressure changes on graph paper. Very useful for spotting trends.
Okay, so pressure is the weight. What about the movement? Wind?
Wind, simply put, it's air moving horizontally.
Why does it move?
It's nature trying to balance things out. Air flows from areas of high pressure towards areas of low pressure.
Trying to even out that weight difference.
Exactly. And we have different words for it depending on how strong it is.
Like a gust.
A gust is a sudden, brief burst of strong wind. A storm is much bigger, a violent disturbance, strong winds, usually rain, thunder.
Pleasant.
No. But then you have a breeze. That's a light, gentle wind. Often feels really nice, especially on a hot day.
The source said soothing is breeze, harsh is wind.
That's a good way to put it. And a breeze is usually silent, whereas you can often hear wind.
And sea breeze, land breeze.
Right. Sea breeze blows from the cooler sea towards the warmer land during the day. Land breeze is the opposite, blowing from the cooling land towards the warmer sea at night.
How do we know which way it's blowing?
With a wind vane, sometimes called a weather vane, it has an arrow that points into the wind.
So if it points east.
It means the wind is coming from the east, an easterly wind.
Got it. And speed. How fast is it?
That's measured by an anemometer, those things you see with cups spinning around.
Ah, yes.
The faster they spin, the faster the wind. And again, there's an anemograph for continuous recording of speed.
What units for speed? Kilometers per hour.
Sometimes, but often in knots. 1 knot is 1 nautical mile per hour. A nautical mile is a bit longer than a regular mile, about 1.85 kilometers.
By knots.
It's standard for navigation ships, airplanes. There's also the Beaufort scale, which estimates wind based on how the sea looks or effects on land.
And local winds, like the Lu.
Yes. The Lu is a famous hot, dry wind in northwestern India during summer. There are many others globally: Mistral, Chinook, Bora. Local geography creates unique wind patterns.
Fascinating.
Oh.
Okay, from moving air to water in the air.
Yeah.
Humidity.
Humidity, yes. Basically, the amount of invisible water vapor present in the atmosphere.
Where does it come from?
Mostly evaporation from water bodies, oceans, lakes, rivers. Plants also release moisture through transpiration.
And it varies a lot.
Oh, constantly. Place to place, time to time, and it's very closely linked to temperature.
How so?
Warmer air can hold more moisture. So generally, higher temperatures allow for more evaporation and potentially higher humidity. Cooler air holds less.
How is it measured?
The standard instrument is a dry and wet bulb thermometer. It uses two thermometers. One measures the normal air temperature, dry bulb. The other has its bulb covered in a wet wick, wet bulb.
And the difference tells you the humidity.
Exactly.
Right.
Evaporation from the wet wick cools that thermometer. The amount of cooling depends on how much moisture is already in the air. There are also automatic hygrometers.
And there are different types of humidity.
Two main ways to express it. Absolute humidity is the actual mass of water vapor in a given volume of air, like grams per cubic meter.
So the actual,
Right. But what you usually hear in forecasts is relative humidity.
the percentage one.
Yes, it's a ratio. It compares the actual amount of moisture in the air to the maximum amount the air could possibly hold at that specific temperature.
So 100% relative humidity means.
Means the air is fully saturated. It can't hold any more water vapor at that temperature. That's when you might get fog or dew or rain.
Ah, okay. High relative humidity feels sticky, right?
It does, because it makes it harder for our sweat to evaporate and cool us down. A humid 30 degrees can feel much worse than a dry 40 degrees.
That makes total sense. So that feeling of saturation, that leads us to condensation.
Exactly. Condensation is the process where that invisible water vapor turns back into visible liquid water droplets.
When does that happen?
It happens when air cools down to its dew point temperature, the point where relative humidity reaches 100%. The air simply has to release some moisture.
And we see this. How?
In many ways, the most obvious are clouds. Clouds form high up when water vapor condenses around tiny particles, dust, salt, pollen forming microscopic droplets, or ice crystals light enough to float. Billions together make a visible cloud.
Okay, what else?
Dew. Those droplets on the grass on a cool morning, that's water vapor from the air condensing directly onto the cool surface of the grass blades.
Lovely, but wet feet.
Yes. And if that surface is below freezing when condensation happens, you get frost, basically frozen dew, ice crystals forming directly.
We see that in winter or high up.
Exactly. And then closer to the ground, fog. Fog is essentially a cloud that forms right down near the land or over water. Reduces visibility significantly.
And mist.
Mist is similar to fog, but the water droplets are finer, and visibility is generally better than in thick fog. Think of it as lighter fog.
So clouds are condensation happening way up high. But you said not all clouds bring rain?
That's right. Cloud type matters a lot. Meteorologists classify them based on altitude and appearance, which tells us a lot about potential precipitation.
Okay, break it down for us.
Broadly, four main types. Way up high, 6,000 to 12,000 meters, you have cirrus clouds.
The thin, wispy ones.
Exactly. Made of ice crystals. They look feathery, beautiful, but they're dry. No rain from cirrus.
Okay, lower down.
Medium altitudes, maybe 2,000 to 6,000 meters, you get cumulus clouds. These are the puffy, cotton ball-like clouds.
The ones kids draw.
Often, yes. They can grow quite tall and dense, though, and can produce heavy showers, sometimes thunderstorms if they build up enough.
Right, and even lower.
Below 2,000 meters, you find stratus clouds. These are more like flat gray sheets covering the sky. They often bring light, steady drizzle.
Dreary weather clouds.
Often, yes. And then there are nimbus clouds. The name nimbus means rain-bearing. These are also low-level, typically below 2,000 meters, but they are very thick, dark, and heavy-looking.
The serious rain clouds.
Definitely. Nimbus clouds bring continuous rain or snow. Think of cumulonimbus, thunderstorm clouds, or nimbus stratus, steady rain clouds.
Knowing the types really helps read the sky.
Okay, so that leads directly to the main event, precipitation. The final step, yes. When those condensed water droplets or ice crystals in the clouds grow large and heavy enough,
Gravity wins.
gravity wins, they fall to Earth. That's precipitation, and it comes in several forms.
Like rain, obviously.
Rainfall is the most common, liquid water drops. If the drops are really tiny, less than about 0.5 millimeter, we call it drizzle.
Okay.
And rainfall itself can form in different ways. Our sources mention convectional, relief, and cyclonic rainfall, depending on what causes the air to rise and cool.
What if it's cold?
If the atmospheric temperature where the cloud forms, and often below it, is below freezing, 0 degrees C or 32 degrees Fahrenheit, the water vapor crystallizes directly into ice. That falls as snowfall.
Beautiful, but can be disruptive.
Very true. Then there's sleet. This is basically frozen raindrops. Rain forms, but then falls through a layer of air that's below freezing on the way down.
So ice pellets.
Yes. And then the really dramatic one, hailstones. Yes, they can cause damage. Hail forms in strong thunderstorms with powerful updrafts. Raindrops get carried way up high into freezing zones, freeze, start to fall, get coated in more water, get swept up again.
Building up layers.
Exactly. They grow like onions, sometimes getting quite large before they finally become too heavy for the updrafts and fall to the ground as hard pellets of ice.
Wow. How do we measure how much rain fell?
With a rain gauge. It's usually a simple cylinder with a funnel at the top that collects the rain and directs it into a narrower, graduated measuring jar inside.
So you just read the level.
You read the level typically once a day. Placement is key, though.
Why?
You need it in an open area, away from trees or buildings that could block rain or cause extra water to drip in, and usually raised slightly off the ground so splashes don't add to the measurement.
Makes sense. Okay, so we've gone through all these elements: temperature, pressure, wind, humidity, clouds, precipitation. How do meteorologists actually use all this information together? How does it become a forecast?
That's where weather maps come in. They're essential tools.
What are they exactly?
A weather map is basically a geographical map showing meteorological data for a specific area at a specific time. It uses standard symbols to represent all those elements we've discussed.
Like a visual summary of the weather.
Exactly. It allows meteorologists to see the big picture, identify weather systems, areas of high and low pressure, fronts where it's raining, windy, etc., and track how they're moving. That's the basis of forecasting.
Are there key features on these maps we should know about?
Definitely. Two very important types of lines you often see are isohyets and isotherms.
ISO what?
Ha! Isohyets. Iso means equal. Hyet relates to rain. So isohyets are lines connecting all the places on the map that receive the same amount of rainfall over a certain period.
Ah, so you can quickly see where it rained the most, or at least.
Precisely. Shows rainfall distribution. And isotherms, therm, relating to temperature connect places having the exact same temperature at that specific time.
So you see temperature patterns at a glance.
Right. You can easily spot warmer and colder regions. Our sources had an example showing isotherms for India in January, clearly illustrating how these maps make the data visual and understandable.
Okay, wow. We have covered a lot of ground here, from that basic weather-climate difference to all these intricate elements and how they're measured and mapped.
What a system, isn't it?
It really is. Let's maybe just pause and quickly recap the absolute key takeaways for everyone listening.
Good idea. So the absolute core distinction. Climate is the long-term personality, the average weather over 30, 35 years. Stable.
Right.
Weather is this short-term mood. The atmospheric conditions right now or very recently, always changing.
Mood versus personality. Got it.
Then we looked at the main elements of weather. Temperature, air pressure, wind, humidity, precipitation, plus sunshine and clouds.
And the tools to measure them.
Yes. Thermometer, barometer, wind vane, anemometer, hygrometer, rain gauge, each designed for a specific element.
And how water vapor turns visible.
Through condensation, forming clouds, dew, frost, fog, and mist.
And finally, how understanding all this allows for weather forecasting.
Which is absolutely crucial for safety, for planning. From sailing and farming to launching rockets and preparing for storms, it touches almost everything.
It really does. So thinking about this whole complex, constant dance between weather and climate, how it shapes our small daily choices and our huge collective efforts, it leaves me wondering, and maybe leaves you wondering too, what's one specific aspect of weather or climate, maybe clouds or pressure, or even just the forecast itself that you now see in a completely new light after this discussion?
That's a good question to ponder.
And how might that new perspective change, even slightly, how you interact with the world around you? Something to think about.
Indeed.
Thank you for joining us on this deep dive into weather and climate. We hope you feel a bit more informed and maybe even a bit more connected to the incredible atmosphere that surrounds us all.